Planck Institute for Mathematics and the Science. He's also part-time professor at the Santa Fe Institute and also at the University of Leipzig. And we are now here to talk about information geometric approaches to complexity.
So first of all, thank you very much for organizing this nice conference and for inviting me to give a lecture here. So I'm going to promote the geometric approach to complexity theory. I will present you the main idea, the results that we have obtained, and also some problems associated with this approach. So I will start with the main idea. It will become immediately clear what I mean by complexity. And I will have a specific formalization of that main idea and study the maximization problem of complexity. I will specify systems that have maximal complexity and relate this to entanglement and also to the complexity of Markov chains, which is related to an approach to consciousness by Tononi. So here's the main concept. It goes back to Aristotle. The whole is more than the sum of its parts. We already heard this in the previous talk. So complex systems are systems where the collective behavior of their parts entails emergence of properties that can hardly, if at all, be inferred from properties of the parts. So, and here's the geometric way I want to model this. So this set here, this geometric object describes the set of all, so this is a qualitative picture, the set of all systems, denoted by S here. So if you talk about the sum of parts, I associate with it two maps. One is taking the system and taking it into decomposing it into its parts. So this is the first map, so that would be the parts. D of S is the set of parts, and then we have to compose them again to get the sum of the parts. So that's the idea. And if you do that, clearly the image of this composition, D and then C, is a subset of the set of all systems. So that's the denoted here by this circle. And it coincides with the set of those systems that are equal to the sum of their parts. So that would be the set of systems that have no complexity. So the idea is to quantify the complexity simply as the distance from being non-complex. So that's the general idea. The complexity of the system is the distance of the original system S from P of S, which is the composition of these two maps here. So from the sum of its parts. This is exactly what this phrase says here. It's the distance of the system from being the sum of its parts. And we cannot take any distance measure here. It has to be compatible with this kind of projection here. So that's a natural requirement here, that if we project in a different way, if we take the minimal distance, we will find a point in the set of non-complex systems which basically realizes, which is exactly the sum of the parts of that system. So this is a kind of consistency property for that distance measure.
Could be, if we understand the D and C operator, can you just very briefly?
This is a pseudo-formal picture here. So these are symbols that stand for some idea, but they are not formalized.
Okay, so you are going to formalize.
I'm going to show you one instance of formalizing it. And so if you talk about the sum of the parts, this this way of thinking about it, this geometric way of thinking about it, I find it very natural. But there are many instances to formalize it, and I'm going to show you one way to formalize it. Okay?
S prime.
S prime. So S prime is taken, so you take the distance of the original system, S, and you take a non-complex system, S prime. So S prime is taken from the set of non-complex systems, and then you compute the minimal distance from that set. So that's the usual way to compute the distance from a set. So we measure the distance of the system from the set of non-complex systems.
So this is a requirement on the distance metric.
This equality would be a requirement. That would be a requirement. And that, excuse me, you were continuing.
S prime is on the equator.
Not on the, that's a two-dimensional thing. Yeah, yeah, exactly. So that's just an illustration. So we have some subset, it can be more complicated, of course. And it's the image of this composition of the sum of the parts. So you get this set of non-complex systems and you measure the distance from that set. Okay? And that was the starting point, how to formalize this theory of complexity. And that was also the starting point to think about measures, distance measures, d, which satisfy such a condition. And that initiated also my interest in divergence functions in information geometry. And I have some papers with Shunichi Amari, who is the founder of information geometry, on that subject. So the notion of a canonical distance measure or divergence becomes very important here. So, but let me come, so that's, as I said, that's a general approach, general conceptual approach to complexity. And here's one instance. This is an example, a very simple example, which actually convinced me to use the formalism of information geometry. So this is very simple, but becomes more concrete now. This is one instance of the approach that I have shown before. So let's consider two binary nodes. So we have state space 0, 0, 1, 0, 0, 1, and 1, 1. This whole thing is the simplex of probability distributions on these four elementary events. Okay, so the corners of this set are exactly the Dirac measures concentrated on these four configurations. Now this surface here, this two-dimensional surface, is the set of all probability distributions for which x and y are independent. So it's defined here. So it's a set of all q. Q are the points in the simplex, in the full simplex here, for which q of x comma y equals q of x times q of y, times q of y. So this is a two-dimensional surface, and this is the surface of those probability distributions that are completely determined by their parts, in the sense that if we know the marginal of x, if we know the marginal of y, then we know the full distribution. So this is the set of distributions that are not more than the sum of their parts. So that would correspond to the non-complex systems. Now, the idea is to measure and obviously, if we have a general probability distribution, we would like to consider the sum of its parts, which would be this point here, being the product of the marginals. Okay? So that's something that I consider very natural, to get the product of the marginals. Now, if you take an arbitrary probability distribution and you compute the distance from this set here, from this two-dimensional set, so by taking the infimum, you can do it with many distance measures, and I did this. I did this with the L2 distance, L1 distance, everything. You never get the product of the marginals, except for one choice, namely Kullback-Leibler divergence. If you take the Kullback-Leibler divergence, it's like it's really very distinguished distance-like measure. It gives you exactly the product of the marginals. So this is why I was convinced that, at least in this setting, we have to choose the Kullback-Leibler divergence in order to measure the complexity, which is the distance of the system from being nothing but the sum of its parts, the product of marginals. And so the nice thing about it is that you get as the distance, so that's the distance from the set F. F is this two-dimensional manifold here. You get the mutual information, which also plays an important role, a very important role in information theory. So that's another argument to use the Kullback-Leibler divergence. So in other words, this consistency that I was requiring in the previous slide is satisfied for the Kullback-Leibler divergence in this context. So I started with this example and made a whole story out of it, which I'm going to tell you here. So, but before I continue, I want to tell you more about the structure of information geometry. So this is very similar to projections in, let's say, RD, yeah, or Rn. When you have a point and you project onto a subspace, you can choose the point in that subspace that minimizes the distance. This is exactly this approach, but there is a second.
Is the perpendicular projection?
Yes, so exactly. So there are two ways to describe it. One is with the distance-based projection, minimizing the distance, and another one using a geodesic, which orthogonally intersects the space. And you can actually extend the theory by exactly that idea. The problem is now you need a notion of inner product, you need a notion of a straight line, and also a straight line in that manifold. And that's what information geometry gives you. This is a really very concise summary of the structure of information geometry. So if you use the Fisher metric, which is defined here, by the way, I'm telling you this, but I'm not going to use this anymore. This is just to tell you, to inform you about the general structure of information geometry. So this is the inner product between two vectors in the simplex, A and B, is almost a canonical inner product in Rn, but you have to weight it, multiply this each summand here by 1 over P of x. So it really depends on the underlying point here. So this is called the Fisher metric. If you take the Fisher metric, if you take this notion of combining points in the simplex, which is 1 minus d times p plus d mod q, it's this line here. And if you take this way of combining them, it's basically not additive but multiplicative, but again with 1 minus d the exponent and t and the other exponent, you get this curve, but you have to renormalize it because that object is not a probability distribution anymore. So if you renormalize, you get this curve. And it turns out that these kinds of geodesics can be described by the so-called M connection, mixture connection. For those of you who know Riemannian geometry, it's an affine connection, which gives you the geodesics. And the E connection, the exponential connection. And they are dual with respect to each other. So we have a structure here consisting of a Riemannian metric, an affine connection, and a dual affine connection. And this triplet, this is the basis of information geometry. And it turns out if you make this choice here, then the distance-based projection, where you take the Kullback-Leibler divergence, so if I project with respect to the distance, the minimizing distance, the point that minimizes the distance, is exactly the point that where the geodesic intersects this surface orthogonally with respect to the Riemannian metric. So again, Hilbert space theory or projections in Rn become equivalent here, whether you take the distance or the geodesic. It's the same thing. So that's all I want to say about information geometry. Let me now continue. That was the main example. I'm sorry for the slides, so it's just to fix notation here. So V is again, as in the previous talk, a set of nodes. It's a finite set. XV is the state set of nodes. I will mainly use plus minus 1, also as the previous talk. XA would be the configuration set, the set of configurations on A. So what do we need here? So the thing is, I need the interaction space on A. I will give you an example which illustrates this. And the pure interaction space, and that's the most important thing here, this part. So, as I said, a complex system is more than the sum of its parts. But I didn't tell you what the parts are. And I'm not going to tell you what the parts are because I don't know. That's a fundamental problem in systems theory, to figure out what the parts are. We start here with the definition of a part. We say the system, we have the system, and we say that a particular set of subsets is the set of parts. It's denoted by A here. So this is really a set of parts, and it has the structure that if you take the union of all parts, it gives you the full set. And if you have a part and you take a subset of that part, it's again a part. So that's a technical requirement for the set of the parts. And you can actually okay, I wanted to write something down because the formulas are very complicated to explain these things. So what we want to have, let's say you take the logarithm of a probability distribution dependent on n variables, and you can expand this. You start with a constant, which is determined by the normalization. Then you have some parameter, let's say theta I, xi. This is called in physics the magnetization. Then you have pairwise interaction, theta ij. This corresponds to the wij's that we saw in the previous talk. And you can continue theta ijk, xi, xj, xk. So these are called the pure interaction terms when you expand the logarithmic probability distribution. And these pure interaction terms span these spaces here. Okay? For each subset, you have such a monomial, so that would be the subset A equals ij. Okay? So this is the subset ij, and that's the pure interaction on ij, and this is a one-dimensional subspace. So that would correspond to this, where A equals ij. And you can do this for all subsets. So you have seen this surface for the product distributions. Now you can actually extend this notion of this manifold to an arbitrary set of subsets. So you have the set of subsets here, and you consider this a family of distributions, which is Gibbs-Boltzmann kind distributions, where f is taken as a function in these spaces that I have defined before. So which means if you expand the logarithm of probability distribution, only terms that live on the set of subsets appear in this expansion. All the others are zero. This is exactly how this is defined. And we have two canonical choices here for the sets of subsets. One is if we have really a network, a graph, we usually choose the set of cliques as being the set of subsets. It has reasons coming from graphical models theory and Hamassi-Clifford theorem, but I'm not going into the details of this. And the second choice is where you fix the interaction order. That would correspond to, so this K here is basically the order of the interaction. So if K is 3, you would stop the expansion here. If K is 2, you would stop it here. Okay? So you have here an increasing a family of such manifolds, which increases when you increase K, where you include more and more interactions into the system. So these are the two examples I'm going to consider. Now, I said I do the same thing as I did before, so the system displays some complexity if it's different from its projection onto this set here, okay? And I define, as I have done before, the A complexity, where A is the set of parts, simply as the distance from the corresponding family here. So it's like exactly the same thing that I did before, but now I don't consider independence, complete independence, they are allowed to overlap. And which sets I consider that are allowed to overlap is exactly given by this A here. Okay? So I can predefine the set of subsets, define such a family, and measure the distance from that family. And for this special case, that's a canonical example.
So in the sets in A are not disjoint.
They are not disjoint. They are overlapping. That makes the whole thing complicated. It's not complicated in this example if I consider the elementary, the subsets of size 1 as forming this full set. It's this one here. That is really the independence case, where I measure the distance of the full distribution from the product of its marginals. And this has a name, it's called the multi-information. So there, in that case, you can actually compute this distance explicitly, and it's simply the sum of the marginal entropies minus the full entropy, in that case. But whenever you have overlapping sets, it becomes more complicated. It's not trivial anymore. But this is an example that a reference example. So now, when you maximize this, what happens is the following. If you maximize the complexity, this means in the simplex you maximize the distance from that family. And intuitively, as you see here, you would expect that the maximizers end up at the boundary of this simplex. So being at the boundary means that the support is reduced. So you cannot have all configurations having positive probability. Some of them have to have zero probability. And this is one of the main theorems. It turns out that this reduction of the support is huge. So whenever you have, so let's say P is a local maximizer of that distance, so of the complexity. You can estimate the support of that distribution. This is those configurations that have non-zero probability by the dimension of that family E plus 1. And that's counterintuitive somehow. I found it very counterintuitive. So let's say you have 1,000 neurons. Let's say they can have state 0 or 1. So you would have 2 to the 1,000 minus 1 dimensional simplex. Okay? Huge dimensional simplex. Now, if you have a one-dimensional curve, exponential family, sitting in that simplex, and you measure you maximize the distance from that curve, it turns out that the maximizers of that distance will lie in two-dimensional faces of that, in one-dimensional faces, because the support is then 1. So this is explained here. So what does this theorem imply? Let's first of all take E. These are really trivial examples, but they highlight the point very nicely. So let's say E is really 1 point. It's the center of the simplex. It is an exponential family. That's the exponential family which has no component here, just a constant. It gives you the center. You maximize the distance. The dimension of that point is of course 0. So you plug in 0. The support is upper bounded by 0 plus 1, so by 1. Which means that the maximizers of the distance from that point can only be these points, the individual points. Okay, so they will be Dirac measures. Now let's go to 1. If you have a one-dimensional exponential family, the upper bound of the support is 2. And you see it here. So that's a maximizer, and this is a maximizer of the distance. And when you are here, the support is 2. It's supported by this point and by this point. The strange thing, or the surprising thing is that this result, this is a two-dimensional picture. it does not change if I go to 2 to the 1000 minus 1 dimensional simplex. It will remain the same situation. That's the implication of this theorem. So that was very surprising to me. It's a kind of simplicity result for complex systems. So when you maximize the complexity, in the limit they become, these systems become quite simple to describe. And it turns out, so the next theorem was my attempt to actually find a nice family in this high dimensional simplex, which allows me to reach all the maximizers. And so the question, what is the lowest dimension to choose so that I can reach all the maximizers? The idea that I had is, if I have a neural network, binary nodes, and they are interacting somehow, so how should I define parameterize the system so that I can reach, that the system can generate the most complex patterns? So that was the idea, and it turns out that based on this support bound, you can actually find an exponential family of dimension 3D plus 2. Actually, later I could reduce that. It's 2D plus 2 that contains all the maximizers of the distance. I want to give you the next slide what that means for binary nodes, coming back to the neurons. So let's say this is just 2, so that's the state space of each node. Here we are maximizing the multi-information, so the distance from the product distributions. Okay? So if this is 2, 2 minus 1 gives 1, so you have here the number of nodes plus 1. Number of nodes plus 1. So just to write down this example. So let's say we have V cardinality equals 1000. So the state space will be, so the support of any distribution could be 2 to the 1000 is huge, but we know that it's 1000 plus 1. So for each maximizer, support of P will be smaller than or equal to 1000 plus 1, which is much smaller than 2 to the 1000. So it's a strong reduction, and I can find so that's the second part, I can find a family in this huge dimensional space, a nice exponential family of dimension 2002, sitting in this 2 to the 1000 minus 1 dimensional simplex, which reaches all the local maximizers of the multi-information of that distance. So that was quite surprising. But then I said, okay, this family, this low dimensional family is an abstract thing. Can I come up with more concrete exponential families? And I asked the more refined question: what is the minimal interaction in the system, order of interaction in the system that allows me to generate maximal multi-information, maximal complexity? So that was my next question. And it turns out that the pairwise interaction, so the family where I basically remove all the terms, just consider up to this order, the family that is generated by going through all the parameters theta I and theta ij is already enough to generate all global maximizers of the multi-information. So that was one result that we had. So pairwise interaction is in this regard, in order to generate maximal complexity, sufficient. But this refers to the global maximizers. I wanted also to have bound for the local maximizers. And it turns out that pairwise interaction is not sufficient anymore, and it depends on the number of nodes. So here's a list. That's a result of my former PhD student. And here's an implication of that more general result. So if I have 10 binary nodes, then interaction order 4 is sufficient to capture all, to generate all maximizers of the multi-information. If I have 100 binary nodes, interaction order 7 is sufficient. With 1000, interaction order 10, and so on. Okay? It's still, so we get the bound for the sufficiency of interaction that we actually need in order to generate maximal complexity. Okay? And but now I'm going to refer to one problem associated with this. Let me phrase this in the context of this theorem. So pairwise interaction is sufficient to generate all global maximizers of the complexity. Remember, the complexity is the amount to which, the extent to which the whole is more than the sum of its parts. This theorem says that if we maximize the extent to which the system is more than the sum of its parts, it becomes nothing more than the sum of its parts of size 2. There is some kind of contradiction. So so you maximize the distance, you want to be more than the sum of its parts, and you end up being not more than the sum of the parts of size 2. Okay? And that's something that some people consider contradicting. And we did some work on that, how to resolve this, but I'm not going into the details of that. But I just wanted, I said there is some problem here, and we did a few papers working on a modification of this approach in order not to get this contradiction here. I have to admit I still don't understand that if there is a problem with it or not. It has some flavor of a problem. But let me outline what we did. So we took the whole idea and applied this to density matrices, and it's related to the first talk that we had. So these are 2 slides just, and the paper that recently appeared. So we extended the whole thing to density matrices. Consider a finite dimensional Hilbert space with complex dimension n. The functions that we have here, the logarithm of p, and the interaction terms there, they correspond to b of h, which is the set of linear operators on the Hilbert space. So this is the self, so these are the observables, which are the self-adjoint elements of this set here. And then instead of considering the simplex of probability distributions, we consider the set of all density matrices, which are those matrices that are positive and have trace 1. So this is the full set of density matrices, and then we stratify this set of density matrices according to the rank. R denotes the rank. So SR is simply the set of density matrices with rank R. And you can actually compute the dimension of SR. It has this dimension, and with the set of all SRs, you get this nice stratification of the full density, the space of all density matrices. So basically, you start with the pure states for R equals 1, and then you go, you continue for rank 2 matrices and so on. So you get a full stratification of the density matrices. So in a classical probability, it's not that nice. So there you have the support. You start with support 1, which is basically, so this point, and this point would correspond to S index 1. this edge, and this edge would correspond to S index 2. And this would correspond to S index 3, which are nice families, which are nice manifolds in the context of density matrices. And the Kullback-Leibler divergence translates to the von Neumann relative entropy. Here it's defined here. The exponential family is these nice families that I have shown before, have also this structure. I'm not going into the details. I just want to give you the information that you get the same result. If you maximize the distance of an arbitrary density matrix from an exponential family, you have again the rank bound. So the rank plays the role of the support. And again, the rank is upper bounded by the dimension of the underlying exponential family plus 1. Okay? So again, you get a strong reduction of the support, if you wish. And this can be applied to the multi-information. That's the multi-information, the non-commutative multi-information version. So the rank of a density operator that maximizes the distance from the product density operators is upper bounded by this quantity. And so these are results that you can read in this article here. It's based on the dissertation of Stefan Weiss. And the reason why I'm mentioning this is the connection to entanglement. So Vedral introduced, and colleagues introduced a measure for entanglement many years ago, 1997, which is very similar to my complexity idea. So instead of measuring the distance of a density matrix from the set of product matrices, which I am doing here, they measure the distance of a density matrix from the convex hull of the product density matrices, which is smaller than the measure that I get here. So the measure that we get here is, so to say, the total correlation. It could be decomposed into the quantum entanglement, as Vedral and collaborators are defining, plus the classical correlation. The problem is that the Pythagorean theorem does not hold here, that you don't get a clean decomposition. I can tell you, so from the information geometric point of view, it's a more intricate thing. The only thing I want to say here is that this measure that I'm maximizing here is larger than the quantum entanglement defined by Vedral. But I have the feeling that these methods can also be applied to his context. Now let me come to the last part, the complexity of Markov chains. How many minutes? 5, okay. So I started with probability distributions. I told you the story there. I did something with the density matrices in the last 2 slides. I told you the story there. Now I'm coming to Markov chains. Okay? There you can do the same thing. So if you have a Markov chain described by transition probability distributions, you can actually expand, apply it, and compute the probability distribution of a sequence x1 to xn simply by this product here, starting with some initial distribution. And with respect to a second Markov transition matrix, you can do the same thing, and then you measure the distance of this whole thing from this whole thing in terms of the Kullback-Leibler divergence. So the thing is, you have to renormalize, and this object here converges to this Kullback-Leibler divergence. So the reason I'm telling this is that it was not obvious to me, not immediately obvious, how to measure the distance between 2 stochastic matrices. But there is a way to do it, and this is the way. So that's the formula that you end up. So basically you measure the distance, the Kullback-Leibler divergence of the stochastic matrix P and Q according to this, and you weight it with respect to the stationary distribution of this stochastic matrix. That's the idea. And now, let's take the distance from being not more than the sum of the parts. So the distance from the non-complex systems. What are the non-complex systems? This is described here. So I'm doing this for 2 nodes just to highlight the main results here. So let's say you have x and y and they make transition to x prime, y prime, and we would consider them to be independent or non-complex if they are simply 2 isolated Markov chains. So no interaction. So this is described by this graph. And I measure simply the distance of this thing from the set of all those Markov transition kernels that have this structure. So again, the same definition, and luckily you can actually compute that definition. You can compute the projection as in the case where you have product distributions, you can project onto the product distributions. And we get a very similar formula here. So it's the sum of the individual conditional entropies minus the global conditional entropy. And it has also this nice property that if the transition kernel is adapted to a graph, so if we have a network structure, so that the joint distribution has this structure, then the complexity that we compute is nothing but can be decomposed into local information flows from the parents of each node I into the node I. So this is also why I found it very interesting. So the full complexity is nothing but the sum of local information flows for each node. You sum them up. So that's very nice. And I was interested in this because of the Infomax principle in computational neuroscience. So now it turns out that the same idea has been used by Giulio Tononi in his formalization of consciousness. So completely different field, but the same idea. So the underlying idea is the following. When we have a conscious experience, the conscious experience is a unified experience. It's basically, you cannot decompose it in 2 experiences. So that's the characteristics of conscious experience. And this is why he also considered the same measure, but has it's not just this consideration, it's a whole construction, it's a whole theory. I would have to tell you more about it. So instead of talking about complexity, he talks about information integration. And the notion of information integration is very essential for his consciousness theory. And now people have formalized requirements. So phi is the measure that is basically phi corresponds to consciousness. The larger phi, the stronger is the conscious experience. That's the idea. And phi is technically referred to as information integration, but there are many definitions of information integration. So recently, people who previously collaborated with Tononi said that phi should satisfy the information integration, so it should satisfy 2 conditions. First of all, it should be greater or equal to 0. It shouldn't be negative. So I mean, nobody would say that there is negative conscious experience. So it must be positive, and it should be, the information integration should be upper bounded by the information flow in time. So information integration in space shouldn't be larger than information integration in time, intuitively speaking. So, and then they tested my approach to whether or not it satisfies these conditions. So if you take the complexity that I have defined and try to find out if this is satisfied, clearly the first inequality is satisfied. But it turns out that it's upper bounded by the mutual information plus some additional term. And that has some reason. Okay. So if you want to resolve that, so it doesn't satisfy this inequality here. And one trivial way to resolve this is to actually subtract from the left-hand side this term here. So you would get C of P minus the whole thing here. Then you get a measure which has been also considered in consciousness research, and some people call it synergistic information. The problem is when you have this quantity, it doesn't satisfy the first inequality. So it's very strange. It's difficult to get both inequalities satisfied. And these people who propose this as a requirement for an information integration measure, it's this group here, Oitsumi, Suhia, and Amari. They propose the following thing. They said this additional term that I get, the reason why it gets larger than the mutual information is because when I go from here to the split model, I also remove that edge here. And I shouldn't do that. Because when removing the edge and measuring the distance from a complete split model, I incorporate also the correlations in the output which shouldn't be incorporated. The idea is that the correlations in the output can come from outside the system, and that shouldn't be counted in the whole in the information integration measure. So they measure the distance of this from this. So I call it C modified, and this is a split of second kind. And in this way, you actually get a smaller quantity, and it satisfies all the requirements that we had before. And my last slide shows a comparison. So this is the mutual information in time. So the full state x at time t, full state x at time t plus 1, and you measure the mutual information. That is required to be the upper bound. That's 1. Number 2, this is my original measure. So that's from the split where you remove also the edge in the output. Number 3 is their new measure, where you don't remove the output edge. And then you have this synergistic measure, which, as you see here, can get better. So this is also excluded. And you see here it's fine. My measure and their new measure, information integration measure, that's somewhat okay. And it also shows the same behavior that you would expect from complexity, that it has some maximum, intermediate maximum. So this is the inverse temperature of the system, and it should be 0 for complete randomness and for complete determinism, and in between there should be a maximum. So, but then if you go to this example here, you see that that's the full mutual information in time, and this is my measure, the green one. It exceeds the mutual information in time. This is exactly the argument against my measure, and this is their measure for information integration. And I have to say, this is an ongoing project using information geometry in order to approach meaningful measures for consciousness. So I'm highlighting the consciousness aspect because I have seen talks that are scheduled for tomorrow, I think, on consciousness, and today this was also mentioned a bit. So this is a very concrete theory trying to quantify consciousness without using entanglement. So I want to advertise here the new information geometry journal. I think, yes, so we already accept submissions. The first issue will be in next year. And I want also to advertise our new book, which came out about 1 week ago. And this is the list of papers that I use for my presentation. Thank you very much.
So my question, going for it to be very naive because it's quite heavy stuff. When you started this example of the factorization of the probabilities, immediately in my mind came, why don't you use the copula approach? The copula, you know, but
no, I don't know.
Okay, so that's very, that might be something enriching because this is a mathematical theory that started to develop in 1970, so you use mathematics from the 19th century, 1970, which is a very beautiful mathematical construction that essentially says how do you uniquely construct a multivariate distribution from the margin. So copula is like, it comes from copulate. You make copulates, if you allow me to say, the marginals to create the multivariate distribution. And they are very beautiful rather than actual, there's a unique decomposition and so on. Essentially, what you have been doing is try to see in what circumstances, what are the distance between the, let's say, the true copula and the multiplicative copula. Because of course, when the multivariate is the product of marginal, this is a simple case.
It's not, that's the whole thing.
Yeah, exactly. So, the point of copula is a unique, let's say, representation of the interdependencies, which is independent of the marginal. So it gives rise to an intrinsic measure of dependence. While any other measures are dependent, if they are not copula derived, they are dependent on the marginals. It's not a pure measure of dependence. So I would suggest if you look at the copula approach, that would be a very natural way of measuring complexity.
So I expect that this is, so I don't know that approach, but I expect that this is something very similar, because the thing that you do here is basically the projection is the maximum entropy estimate. So you have the marginals, they are allowed to be overlapping, and you search for the distribution that has the same marginals and maximize the entropy.
So the good thing, I would say, remark is that you can show that you need a Kullback-Leibler measure distance is a copula. Is a copula measure. So it is independent from the marginal. In that sense, it's a good measure. It's one among many. The second remark I wanted to make is when I see your exponential family and this expansion here that you used, as a theoretical physicist and trained in renormalization groups, for example, you immediately react to say, oh, it's a bad decomposition, right? It's a not very efficient decomposition.
Why is that?
Because when you are very, okay, I could return this in a question. Why is it a good decomposition?
So I can tell you. So there are two, from physics, there is one canonical decomposition, where you need the vacuum state, and then you have you need an interaction potential. These monomials form an interaction potential, and the interaction potential is normalized, in the sense of physics, if whenever a state has a vacuum state, which is usually modeled with 0, then that contribution to the interaction potential vanishes. So that's the normalization idea. And there is one distinguished normalized potential for every positive probability distribution.
You think you give me an angle to...
So that's one thing. So the normalized potential thing, and this comes from
okay, I understand.
But this is not the normalized potential. So if we had 0-1 states, that would be the normalized potential. But I assume -1 + 1, and the reason is that if you take the canonical inner product in Rn, then these monomials become orthogonal with respect to the canonical inner product. So you try, there are two ways. You have, the decomposition is not unique if you don't require additional requirements. One is normalized potential, and one is you take an inner product and you want the decomposition to be orthogonal. And this gives you an orthogonal decomposition. Both of them are justified, but all I did in my distance calculations do not require the particular decomposition of the energy. So it's not required. So this is just as an illustration, because the notation was somewhat tricky. This is just as an illustration what I mean by this family, increasing family of exponential families.
So thank you for this clarification. What I'm a bit perturbed is that speaking of very complex system that you essentially start from the vacuum, meaning you have a low coupling perturbation type of approach, where you could imagine to start from the strong coupling, right, from the intrinsically, because essentially each term corresponds to adding and transcending the interaction. What you would say, if I look at fully complex systems, I'm interested to characterize them, you should start from the most strong coupling. So this perturbation expansion on the low coupling.
So what I said, one of the results was that the highest coupling does not contribute to high complexity.
Yeah.
So the coupling strength.
That's the key point. Okay.
So the coupling strength that you, not the strength, the coupling order that you need in order to generate the largest distance from these families is actually very low, and we can give explicit formulas for that. Yeah.
The question? Yeah.
The last part of your talk, consciousness, very interesting. But does the insight about how you describe the integrated substrate, if you like, or how you describe consciousness in terms of integrated information and shared states, does that give you any clue as to what consciousness is? Because it strikes me that
So
it's
do you
a
know?
mathematical tool, really, isn't it? You're looking at consciousness and you're saying, okay, well, if these ideas, I guess, when they measure how integrated consciousness is, if this object requires a lot of integrated information, then that's conscious. But in the neurons, information isn't integrated. You have one neuron, you have another neuron, and they're firing at a particular rate, which encodes a particular tiny bit of information. Does it give you any clue as to what the nature of consciousness might be, and how a conscious state might differ from an unconscious one?
Yes. So I mean, if you, so first of all, I have to say that Tononi himself is not a mathematician. He started exactly with the neuronal substrate, working with Edelman and Spons in the 1990s. And he worked. His main work is on sleep and consciousness, and he's famous for that. Many people react very skeptical. So there are two kinds of people. One say doesn't have anything to do with consciousness, and others say this is exactly how we should go for it. And so he started with that, and he basically, so first of all, when you define it in terms of the dynamics of the system. You can specify those the dynamics that actually gives you the highest information integration. You can do that, but what he does is not this experiment. He does the following: what kind of architecture would I require from a network in order to be able to generate states with high conscious experience, with high information integration? And he comes with principles, he ends up with principles for how to design the network architecture, how to connect the neurons, and he relates this to the brain architecture. And the thalamocortical interaction is is one of his main arguments, that this is exactly an architecture that allows you to have very high information integration. And he distinguished this from network architecture. For example, you can have, I can talk to you and walk and do the same thing, behaviorally equivalent to the Nihat who has actually conscious experience, but with a feed-forward architecture, with no feedbacks and so on. And you can actually prove that this feed-forward architecture, doing the same thing, has no information integration, which he calls then a zombie. So that's a philosophical term. So you can actually pretend to be alive and to behave like a human being without conscious experience. So it's really about the architecture, and he draws conclusions on the architecture of the system. And another person who is Christoph Koch is very famous in this in consciousness research, and he's very convinced by this approach.
But I think we're talking about information from the individual, not information from outside the individual.
So
being the source of consciousness.
yes.
So it depends on my the individual's personal store, and it's maybe perceptual information.
So the way they treat it is it's triggered from outside, but it's mainly the information integration of the system itself. So for example, the main example is a dream. You have consciousness experience in dreams, conscious experiences in dreams. So you have to be, and the way they think about it is that the system is in a dynamical, it's a dynamical system which has high information integration, and this is why you experience consciously when you dream. But I have to say that this is one of the weak points of the theory. I consider it to be a weak point, not to embed the whole thing in a sensory motor loop. It's done, but not in a very systematic way. Until now, they really treat more or less isolated systems. And the last slide, so Oitsumi was a postdoc working in Tononi's group, and he now joined forces, so to say, with Amari, the founder of information geometry, and they tried to find the right measure for phi, for this information integration. So, and it is an idea, it's a general idea. I could tell you more about this, how it's constructed, and how it's based on axioms that Tononi developed. But still, it leaves a lot of freedom for many, many choices of such a measure. And they are trying to develop, so to say, to identify the most natural choice for such a measure of information integration. And the coincidence here is that their measure, the measure of information integration that started, with which Tononi started, is very similar to my measure of complexity. So integration as distance from no integration, complexity as distance from no complexity. It's the same idea, and they try to utilize the formalism of information geometry at the moment, and to formalize it. So I find it very appealing, actually, this idea of to couple information integration with consciousness. But this is the thing: can you prove it? So that's the big problem. So I don't know. Entanglement has been mentioned in your talk.
Yeah.
So would people here, would you consider entanglement to be essential for consciousness, or
No, I
so?
think the case for quantum mechanics being involved in consciousness at all is so weak. It's not science. There's no scientific case for consciousness requiring quantum mechanics to explain. So entanglement, there's no evidence that entanglement is a feature of consciousness.
Okay, then thank you very much.